Welcome everyone. In this lesson, we will be delving into Newton's second law of motion. This fundamental principle in physics is key to understanding how forces influence the motion of objects. This law expressed mathematically as resultant force is equal to ma forms the backbone of classical mechanics. It describes how forces cause objects to accelerate, linking mass, resultant force, and motion in a straightforward way. As we progress, we will uncover how this law explains everyday phenomena from a cyclist pedaling faster to objects slowing down due to resistance. Let's begin by setting our objectives for this lesson. By the end, you should be able to determine the resultant force using free body diagrams. Free body diagrams help us visualize all the forces acting on an object, making it easier to calculate the resultant force. Apply the relation resultant force equal to ma to solve problems. This is the core equation of Newton's second law, linking resultant force, mass, and acceleration. Define linear momentum and explain the principle of its conservation. We will explore what linear momentum is, how it relates to motion, and why it's conserved in isolated systems. Understand the relationship between resultant force and change in momentum. This will tie back to Newton's second law, as resultant force is directly connected to the rate of change of momentum. To better understand Newton's laws, let's consider a simple case study. Imagine John cycling at a constant velocity. This means his speed and direction remain unchanged, resulting in zero acceleration. In such cases, the forces acting on him, like the pushing force and air resistance, are balanced. This aligns with Newton's first law, which states that an object remains in uniform motion unless acted upon by a non-zero resultant force. Here, we see how Newton's first law applies. John's pushing force balances the air resistance. This balance of forces results in zero resultant force, allowing him to maintain constant velocity. When forces are balanced, there is no acceleration. This sets the stage for understanding what happens when forces become unbalanced, leading us into Newton's second law. Newton's second law tells us that the acceleration of an object is directly proportional to the resultant force acting on it and inversely proportional to its mass. Mathematically, resultant force is equal to ma. Now, let's imagine John pedals faster. When the pushing force exceeds the air resistance, there is a non-zero resultant force. This unbalanced force causes a change in velocity or acceleration. This is where Newton's second law comes into play, explaining how an unbalanced force affects motion. In this case, the pushing force exceeds air resistance. So the resultant force, which is the difference between the larger pushing force and the air resistance, causes acceleration in the direction of the pushing force. Conversely, what happens if John stops pedaling? The air resistance becomes the only horizontal force acting on him. Since the only horizontal force acting on John is the air resistance, the resultant force equals the A resistance. This force acts in the opposite direction to his motion, causing him to slow down or decelerate. This highlights an important principle of Newton's second law. When the resultant force is in the direction of an object's motion, the object accelerates. Conversely, if the resultant force acts opposite to the direction of motion, the object decelerates. Newton's second law can be expressed as a mathematical relationship where F resultant equal ma. Here, F resultant is in newtons, mass in kilogram, and acceleration in meter per second square. Here is the formal definition of Newton's second law of motion. For an object of constant mass, the resultant force acting on it is the product of its mass and acceleration. The acceleration is in the same direction as the resultant force. It's crucial to note that the resultant force doesn't arise from acceleration. Instead, the resultant force causes the acceleration. The acceleration always aligns with the direction of the resultant force.